Now, all of this design, right, so far we have talked about processors, memory. The moment we want to sort of expand beyond that, we need to bring in this notion of intellectual property, right, which is the sort of standard industry standard term to it's more or less like saying it's a library of software functions, right, and just like you can buy software, it's also possible to buy IP blocks that are used in hardware. The whole idea of IP though is IP reuse, right. It, it should be possible as a system level designer to make a choice saying I am either going to build this new system on chip completely from scratch, meaning that everything, let's say down to the UART or the SPI interface, my team is going to design and build and verify on their own. The alternative is somebody else has already done the job for you, can't you just buy it, right? What that means is that, in order to do that, you basically need to have some kind of standards that are followed by the different IP blocks, and as long as you follow those standards, it's possible to actually buy an IP from someone else and be reasonably confident that it is going to work well with the system that you are designing and building. Integrating such IP blocks poses many challenges of its own, right? You need to have interface compatibility, as I said, the bus standards and so on come into play. Very often these IPs also tend to have other kinds of issues like clock domain crossings and power domain crossings, right, which we will talk about a little bit later as well. Integrating all of these onto a single chip requires careful floor planning, and at the end of the day now we are getting to the point where we are talking about individual blocks with hundreds of thousands of transistors and many tens or possibly even hundreds of them being integrated into a single chip, right. And as part of that, very often you have different categories of IP. You have so called hard IPs, which are literally given as a complete designed, placed and routed design on silicon, which means that you just literally take it as a black box, and while you are designing your system, you need to mark off one section of the silicon and say this is where this external IP is going to fit. I just have to leave the space for that and stitch it in there finally, because I am not allowed to change anything inside it. Soft IP on the other hand is something slightly different. It's given typically as some kind of RTL code, right, actual Verilog or VHDL code, possibly with some kind of encryption so that it's not possible to go in there and modify it as such. But on the other hand, the synthesis tools are able to take it and do certain optimizations if necessary. Firm IP is a word that's sometimes used for something that lies somewhere in between these two. A company like ARM, for example, pretty much deals entirely with IP. They, until recently at least, did not manufacture any chips of their own. What they do is they design and get either hard or soft IP cores and then license them out to various vendors who integrate them into their own designs. What this means is that for doing this kind of integration, you need very clear interface specifications, and as we will see later, ARM took the lead to some extent on designing formalizing the bus interface that has now more or less become an industry standard and is used widely across the board. It also means you need to be able to perform verification of the chips at their boundaries without being able to go into the design of individual blocks, right? And standardized bus protocols are pretty much the only way you can manage this level of complexity. Now, buses, right, typically what we have over here is we might have something like a CPU, a graphics processing unit, you have a memory, you have DSP, various kinds of modules like this, and there is some kind of a shared bus that basically allows each of these blocks to talk to each other. So GPU can talk to memory, CPU can talk to memory, the DSP can talk to memory, well, DMA also should be going through the shared bus and so on, right. So this is what a traditional bus architecture looks like, and mostly what happens is, well, a couple of things as you can imagine. This shared bus becomes a bottleneck. It also becomes a very long sort of set of wires that need to be routed across the chip. The alternative to that is what's called a network on chip, right, which we will again talk about a little bit more later. And the idea of a network on chip is that rather than having a long set of wires, you actually break up the communication between blocks into a large number of smaller routers or switches that are capable of sending packets of information across from one to the other, right. This has made a significant impact on how larger systems get designed these days. Now, key considerations when you are deciding on something like the bus versus the NOC for a system on chip. come down to various things like, what kind of bandwidth do you need, what kind of latency, in other words, how much time are you willing to accept between the sending data from a processor to when it actually arrives in memory, or the other way around. Power consumption is an increasingly important aspect of SoC design. The communication power actually starts to become significant these days. And you have various things like the routing complexity and the quality of service. Is there any delays that you are going to encounter when you actually start using networks instead of just having single wires, right? So various aspects come into play when you are designing such things. So to sort of put a big picture over here, this is what a typical mobile system on chip looks like today. You would have a CPU cluster which would have some performance cores and some efficiency cores. This is related to that idea of what I call the big dot little architecture, right? Typically the performance cores will be called the big cores and the efficiency cores will be called the little cores. Each core by itself has some L1 cache inside it. By the way, this notation L2 is a common notation to talk about cache, right? The idea being that dollars stand for cache. It's more of a pun if you look at it, right? It's not really CASH, but they use the dollar sign anyway over here. The CHE is more a term for a temporary storage, something that is just kept as a for holding some data until it's used later. And of course, so you have the CPU cluster with its own cache memory out here. Typically, you then have GPUs, which are for general purpose image processing, NPUs these days for neural processing and AI ML applications, ISPs for image signal processing, especially for things like handling the camera interfaces, maybe dynamic compression of the images or real-time conversion from one format to another and so on. Generic digital signal processing, mostly used for audio and similar kinds of applications, and mostly, especially given that it's a mobile SoC, an important part would be the modem, which is the modulator demodulator that is used for communication, right? And this would need to have multiple wireless protocols. It would be the 5G or LTE or 4G/LTE standard, or Wi-Fi, I mean not or but also, right? So it would need to also be able to support Wi-Fi as well as Bluetooth. All of these tend to be an important part of what the modem needs to support. You have a memory subsystem that needs to have memory controllers that can talk to external RAM, the ability to talk to DRAM, the ability to talk to non-volatile flash storage, right? Various kinds of cryptographic accelerators which actually sort of help you with the security both of the system itself as well as for various kinds of communication. And display and multimedia, right? You have video codecs which are usually related to what the image signal processor can do. But as you can imagine, you have a GPU, ISP, display and multimedia. Maybe not all of them on the same chip, but these are common variants that exist in most SoCs. Finally, you need some way of communicating between all of these, and as you can imagine, given the complexity here, a simple shared bus is not really realistic, which is why most modern systems tend to work with NOCs, networks on chip. And of course, the interesting thing is just providing power to all of these or to such a large circuit is by itself a very challenging task, right? So power management controllers by themselves are also a fairly important area of design and play a very important role in the overall working of the system on chip. As you can imagine, there are a few analog components here. The modem would contain analog components. There would be maybe something in the unlikely, but possibly something in the memory controllers, especially in the DDR interfaces and so on, right? High speed interfaces, and of course in power management. But pretty much everything else on this SoC is digital systems, right? So as you can imagine, this is basically the reason why this is in some sense the culmination of this course, right? At the end of the day, you very rarely go in there and just design an individual digital block on its own. What you are doing is you are probably going to be ending up designing some submodule of one of these systems, right? And then seeing that larger and larger teams are required in order to integrate the entire system into one big block. This also leads us to this notion of hardware-software partitioning, right? We need to have some level of partitioning between hardware and software. So the first question is, what is hardware software partitioning? Well, we have hardware implementations that have fixed function blocks and possibly accelerators for certain compute intensive algorithms. And in order to make use of these, we need to have some kind of software which basically says that maybe there's an operating system which runs on a general purpose processor. There is some kind of firmware that is needed for device control, right? And we need both of these things, the hardware and software, to sort of work together, right? Now, why do we want to have this sort of split between hardware and software? Isn't it possible to completely do everything in hardware? I mean, after all, a finite state machine can do any kind of control that you want. It's also fairly inflexible, meaning that once you have designed a finite state machine, it can do whatever task it was designed for, but if you want to change it, you need to go in and redesign the finite state machine. Which is why ultimately, as we saw when we sort of built up towards the processor, in some sense a processor can be seen as a programmable finite state machine. Right? It allows you to sort of extend the idea of a finite state machine in certain ways. Now, why we do this is we want the hardware to give us good performance, power and so on, but at the same time we want software that allows us to develop in a reasonable amount of time and also give us flexibility. Which means that finally, from the designer's point of view, a number of co-optimization approaches and requirements come into play that you need to keep in mind when you are actually building a large system. So to sort of summarize this discussion of SoCs, right, SoCs represent the integration of entire electronic systems on a single chip. Modern SoCs have a lot of different processing element types, heterogeneous elements, right, primarily because they also have to deal with different kinds of workloads. The memory hierarchy and interconnect design are critical, right, from the point of view of system performance. Without IP reuse, modern SoCs would not be possible, right. So the whole notion of how we standardize on IP interfaces and then on certain kinds of IP protocols and so on, right, is essential to be able to manage the complexity that we are dealing with. In order to make use of these IP, you need to have both hardware and software and co-designing them. In other words, the software has to take into account what the hardware is capable of, and the hardware should sort of learn from what the software is having difficulty with, and then maybe you introduce new features in the hardware that allow certain kinds of software functionality to improve. Moving towards the future, what we can increasingly expect to see are so-called domain-specific architectures, where we find that our systems are getting tuned towards specific kinds of applications. Nowadays, the biggest trend is of course AI ML. There could be others that come up in the next few years, right? But we are also hitting the limits of what our technology advances can give us, right? Which means that things like 3D integration, having actually multiple layers of silicon tied one on top of another, or chiplets, where we basically break up a silicon die into multiple smaller parts and integrate them in package sort of, right, or at least on a single substrate, are increasingly going to become common.